Good afternoon, everyone. My name is Mohammed Al-Aish, and on behalf of the American Society of Mechanical Engineers, Eastern Saudi Arabia section, I would like to welcome you all to our Ask the Expert webinar series. As always, we invite you all to direct your questions in the chat box, and we'll do our best to accommodate all of your questions. Today is a continuation of our theme on hydrogen and green fuels. We have a special guest, Dr. Mani Sarathy, who is a Senior Manager of Technology and Innovation at NEOM Hydrogen and Green Fuels. He is also an Associate Director of the Clean Combustion Center at KAUST. Dr. Sarathy, thank you very much for joining us today.
Good afternoon, everybody. How are you doing? Nice to be with you.
So before we start off, you wanted to share with us a presentation on the hydrogen, green fuels, and circular carbon economy. So I'll leave the floor to you. Go ahead.
Yes, please. Okay. Thank you, everybody. You'll tell me when you can see the presentation, please. Can you see the presentation?
Yes, Doctor.
Okay. Okay. Good afternoon, everybody. My name is Mani Sarathy. I'm happy to be with you all at the ASME. I'm an associate professor in chemical engineering, but I have an appointment in the Department of Mechanical Engineering as well at KAUST. And also, since my PhD, I did my PhD in the Department of Mechanical Engineering at the University of Toronto. So I'm very much interested and enlightened by the field of mechanical engineering and how it can be used to apply solutions to many different types of problems. So today I'm going to talk a little bit about some of the work I've been doing for the last 1 year at NEOM around hydrogen, green fuels, and also the circular carbon economy. Many of you must have heard about NEOM already. It's not news that we have this region in the northwest of Saudi Arabia that's being developed as a city of the future, or a region of the future. The region of the future will have the cities of the future, but it will also have many other features of future ways of living in urbanization, in nature, in terms of energy, water, the environment. You see here, it's bordered by the Gulf of Aqaba and the Red Sea. And one of the key features of NEOM is that only 5% of this total land is permitted to be developed by man. 95% has to remain as nature, untouched by man. And that 5%, 95% split has a lot of implication on the decisions that's made at NEOM in terms of cities, buildings, urban infrastructure, energy, wind farms, solar farms, industrial applications, tourism, anything you can imagine. And keep this in mind. If you have a space and you can only develop 5% of the land, what kind of decisions would you make for that development? Now, I work in the energy sector within NEOM. And in the energy sector, our goal is to enable the next wave of an energy transition, moving away from conventional fossil-derived energy sources and non-renewable energy to 100% renewables. Now, this is very challenging. This is an ambition that the leadership at NEOM wants. They want us in the energy sector to think, how can we establish an energy ecosystem that's 100% renewables? I myself, given the available technologies today, say this is extremely challenging, perhaps even unrealistic. However, we still have to go through the exercise and identify how close can we actually get to 100%, and at what time frame could we reach actually 100% renewable. In addition, we want to produce 100% of renewable energy for NEOM, for use within NEOM, but we also want to be able to create excess renewable energy, which can be exported around the world as a new type of energy market and energy industry. Why would we want to do this? Well, we see that many sectors in the industry, in society, are looking for renewable energy solutions. Renewable energy solutions that are not based on carbon-based fuels or based on non-renewable energy sources. One of the very important sectors are trucks and cars, passenger vehicles and heavy-duty vehicles, as well as ships. And if we look at this sector, one common way of addressing the decarbonization strategy for automobiles and for trucks which are heavily reliant on petroleum hydrocarbons, is to say that these mobility applications would be electrified fully. Now, the problem with this thinking, we believe, is that we cannot electrify all the vehicles to get, with renewable energy, to get zero carbon emissions in the next 2 decades. And that's what these plots are showing. These plots are showing that even if we have very ambitious scenarios of selling electric vehicles, 100% battery electric vehicles in the year 2040 and 2050, you'll always have a fraction of vehicles sold or on the road, because vehicles have a surface lifetime of 10 to 15 years. You'll always have a fraction of vehicles on the road that have combustion engines. And these combustion engines will be reliant on fossil fuels unless you provide an alternative solution. And if you look at heavy duty trucks on the bottom chart, it's the same. The upper part here of these graphs shows that some fraction of the heavy duty transport vehicles will be reliant on combustion-based technologies, largely driven by fossil fuels today, up until the year 2050. So pure electrification is only part of the solution. Cannot be the complete solution to reach a fully decarbonized or renewable energy-based economy within Saudi or even in Europe, Japan, or around the world. Furthermore, when we look at fully electric solutions, we find that just because you take away the mined fossil fuel from the energy powertrain, you're replacing that with other types of mined minerals and chemicals. And these are things that are used to make the battery, the electrodes, the membranes, all of these things that are required for solar panels for renewable energy, batteries for electric vehicles, electric motors for propulsion systems. And on the bottom of these charts, you see different elements like iron, aluminum, indium, dysprosium, lithium. And on the y-axis is the demand versus the supply ratio. And it shows that many of these minerals have to be supplied 4 to 5 times their current supply in the next 2 to 3 decades. And if we look at even available reserves known today, many of these elements, the known reserves, lie below the projected demand. These fully electric solutions, fully renewable-based solutions are important, but they're going to be constrained both by increasing demand requirements and lack of supply, which requires infrastructure and further development. So one of the things we look at NEOM is what can we do besides just making renewable energy, electricity, and using that to power different sectors? How can we convert this renewable energy to something else which can be transported and utilized in different sectors and not be reliant on technologies that are very dependent on rare minerals or fully battery-driven solutions? And that's where we come upon hydrogen. Hydrogen is a chemical vector or a chemical battery for essentially storing renewable energy and transporting it for utilization in different sectors in a carbon-free or low-carbon scenario. Now, hydrogen is a molecule. It can be used for fuels in transportation. It could be used for power generation. You could use hydrogen for heat in buildings and industry like steel and cement. And you can use hydrogen to make chemicals and also material products. You can also convert hydrogen to things like hydrocarbons when reacted with CO2, and I'll talk about that more later. So you can actually make renewable hydrocarbons using hydrogen. Now the challenge is you got to make this hydrogen from renewable energy for it to be really green, low carbon, and non-fossil based. Conventional hydrocarbon, we call gray hydrogen, is based on the steam reforming of natural gas. You see it here on the right chart. The steam reforming of natural gas costs anywhere from 80 cents to $1 per kilogram of hydrogen. If you want to capture the carbon associated with that process, which many companies like Aramco are looking at, we call this a blue hydrogen, which is fossil-derived hydrogen with carbon capture. The price of that hydrogen goes anywhere up from $1.50 to $3.50 per kilogram. And then if we talk about renewable-based hydrogen, which is where we take renewable energy and do electrolysis of water, the price is anywhere from $3 to $5 today for the producing this green hydrogen. But in the future, the ambition is that with increasing scale up of electrolyzer manufacturing will drive the cost down of green hydrogen. So it actually becomes competitive with the fossil-derived hydrogen pathways. And this is the focus of NEOM. NEOM's focus is entirely on the green hydrogen, renewable-based hydrogen, driving the cost down so that hydrogen can be exported, produced in the kingdom, and exported around the world as a new energy market. So the essential concept is you take renewable electricity based on non-fossil derived sources, you electrolyze water, and you can convert that to hydrogen. That hydrogen could be exported directly, but it has limited potential for export given that it's a gas, and unless you're able to liquefy it, which is very expensive, long distance transfer doesn't become feasible. But rather you can react that hydrogen with captured carbon, with nitrogen, and you can make different types of liquids that are easy to transport and then used in different sectors. So we call these different technologies power to X. X can be hydrogen, it could be a hydrocarbon, it could be ammonia. Anything that's derived from renewable energy using green hydrogen as an intermediate. So NEOM wants to be a leader in power to X and hydrogen supply globally. The location is good, it's on the coast, it's close to the Suez Canal, it can export to Europe and also go down the Red Sea and export to Asia. And many of you might have heard about the largest green hydrogen investment now globally. It's a $5 to $6 billion project between Air Products, Aqua Power, and NEOM. It's titled the NEOM Green Hydrogen Project. And the goal here is to build 4 gigawatts of renewable energy capacity, solar and wind, 2 gigawatts of electrolysis, and then produce 650 tons of green hydrogen per day. And that will be converted to ammonia, which is a chemical acting as a hydrogen carrier on the order of 1.2 million tons per year. Now, this ammonia will be then taken to Europe and to Asia, where it will be cracked back to make hydrogen for powering fuel cell electric vehicles. This plant will be running by 2025, and it'll save significant amount of CO2 emissions by the use of this green hydrogen. Now, this is a commercial project. There's a commercial business case for it, and the technology for it is largely commercialized. However, we have to think in the future, how do we accelerate technology so we can have more similar types of commercial development projects? Right now, the only one that makes sense is green hydrogen to green ammonia. But there's many other things we could do with hydrogen, which today are not so economical from green hydrogen, but we need to develop technologies and innovation to drive the cost down so they become commercializable in the next 10 years. So our hydrogen and green fuels roadmap includes developing new technologies for hydrogen production, conversion of hydrogen to different carriers, ammonia being one of them, but also other types of fuels like methanol, hydrocarbons, as well as chemicals. And then we also want to innovate on the end use applications of hydrogen and its carriers for land mobility and marine mobility. In addition, NEOM wants to be carbon positive meaning that it does not produce new carbon emissions and also removes carbon emissions from the atmosphere. So CO2 capture from point sources and from the air are important. One reason is to give us CO2 to react with the hydrogen to make hydrocarbons, but also we're looking at large scale potential CO2 capture and storage as a way of as a business model for NEOM to sell emission trading certificates for CO2 storage geologically. This is our innovation roadmap. You might know innovation starts at very basic and applied research at low technology readiness levels, and then moves eventually to commercial applications. But this development roadmap takes a lot of time, and it takes strategic thinking in order to become successful. The NEOM Green Hydrogen project making green ammonia is a commercial project. It's based on all technologies that are TRL 9+. However, we want to already start thinking about what will be the next big green hydrogen project and how can we do it cheaper than the one that's going to come in 2025. And for that, we're developing a hydrogen innovation development center. I'll show you some plans for that, where we'll have laboratory testing, pilot scale integration of various hydrogen specific technologies, so we can move them across the technology readiness ladder. And then we're also developing a research institute where we will have expert scientists and partner institutes within Saudi and globally working on basic research for game-changing technologies around hydrogen and CO2 capture and storage. So these are the different themes of focus in all of our hydrogen projects. We're interested in hydrogen production from renewables, conversion of hydrogen to carriers for transport and storage, different types of e-fuels and e-chemicals, as well as end-use applications like fuel cells, combustion engines, hybrid systems, wherever we can use hydrogen and its derivatives economically and more efficiently. Together with these core areas, we need to do carbon capture and utilization. One is to support the production of various fuels and chemicals, and one is also for this eventual emission trading certificate market that NEOM wants to be involved in. And we also see that many of these things here will require improvements in digitalization of these systems and AI. So we're including an entire thrust of integrating digital and AI infrastructure for energy systems, renewable energy systems, together with hydrogen production and storage. I'll show you a short clip about this place that is being developed in NEOM. It's called NEOM Industrial City. You see here, it's a circle. The city is about 30 kilometers or 40 kilometers north of Dubai, which is an existing city just outside of the NEOM region. And what we have here in the middle is the Dubai port, which is an existing port, a shipping port on the west coast of Saudi. And this port now lies within NEOM. It will become a NEOM asset. It'll be expanded to make one of the largest shipping ports on the west coast. And around this port will then be an industrial city, which will have many different things. Down here in the south of this industrial city will be the NEOM Green Hydrogen Project. In the north, we will have the Innovation Development Center and research institutes. You see here, about a third of the city is on land. 2/3 of the city is a floating city on water, which is the urban ambition for this project. Again, this is the NEOM region up here. You see the line. Many of you have heard about the line. The line is the major city where most of NEOM population will live. But together with the line, there'll be a small city in the south. That's the circle. That's the NEOM Industrial City. And I'll try to show a short video here. So this is, it's about 65 kilometers south of the line. Half the city will be on water. 2/3 will be in water. About a third will be on the land. And there'll be a major port with facilities, not only related to energy and hydrogen, but also food, water, digital infrastructure, also things around manufacturing. So one of our goals is, and specific in the hydrogen team, is to develop hydrogen-related technologies, which would eventually lead to businesses that manufacture products and solutions within NEOM for use within Saudi and for export around the world. And this is our Hydrogen Innovation Development Center. It will be completed building by the end of 2022. Right now, what we have is the land. It's been leveled and foundations are being laid. And this will be the rendering of our facility. We'll have hydrogen production on this site. And we will have conversion of hydrogen to methanol. We'll have air capture technology demonstrated. And we'll also have some solutions for converting methanol to gasoline. We'll also take some of the hydrogen and fill it into trailers and have a hydrogen filling station so fuel cell electric buses and trucks can be refueled in NEOM. So our phased approach for the Hydrogen Development Center is here. It's going to be ready by end of 22 and early 2023. Phase 1 is by the end of 2022. We'll have a 20 megawatt electrolyzer. It'll make 9 tons per day of hydrogen. Some of that hydrogen will be stored and sent to filling of vehicles and buses. And then about a quarter of that hydrogen will go to make methanol. Methanol will be made by reacting captured CO2, both from the air and from a point source. to make renewable green methanol. And that methanol, some of it would be stored, and we'll use that stored methanol and send it for marine applications, for powering marine vessels, or also cracking that methanol back to hydrogen for some off-grid applications. In addition, we're working with an industry partner to convert methanol to gasoline. So it'll essentially be the same hydrocarbon composition as your petroleum gasoline, except based entirely on captured CO2 and green hydrogen. And our industry partner aims to take that gasoline and export it to Europe. So our plan is to produce synthetic, low carbon, no carbon fuels. We're working on plans for Fischer-Tropsch-based processes to produce diesel fuel and jet fuel. As I mentioned already, we're doing the methanol to gasoline route by 2023. And we'll also be demonstrating decarbonization of marine engines using methanol and other types of e-fuels. And ultimately, what we want to do is try to work with some partners to develop CO2 capture solutions to make fully carbon neutral or low carbon renewable fuels. This is challenging today because air capture technology is not mature enough and not able to capture enough CO2 for the types of large scale hydrocarbon fuel production facilities we want to make. So right now we rely on largely point source carbon capture like power plants and cement plants, but we need to innovate air capture technology with some partners to really make the lowest carbon fuel possible. And this is probably a 10 to 15 year roadmap. And then finally, we're developing a green maritime propulsion hub. This will be ready by the end of 2023, early 2024. And it's going to be a waterfront facility where we will be entirely focused on fuels and related propulsion systems for large marine applications. So different types of fuel applications for large marine vessels, mainly decarbonizing the engines on those ships, but also coupling them to fuel cell electric powertrains based on hydrogen. Also improvements in the way fueling is done for things like ammonia and hydrogen, improvements in propulsion technologies, after treatment, and the vessel optimization for improved trip efficiency and lower fuel consumption. So I thank you for your time. I'd be happy now to go through a Q&A about anything on this presentation or also anything related.